In our fifth lecture, we're going to go over alcohols. Note that for the next couple lectures, we're going to go into functional groups and reagent reactions for those respective groups. We'll start with alcohols. This will be the shortest one, so it'll ease you into the rest. Starting with nomenclature. To name an alcohol, we replace the E on the parent alkane with an "-ol". So an example would be if a hydroxyl group is present on a butane, we would replace the E on butane and put an "-ol" on it, making butane to butanol. Note that you can have multiple hydroxyl groups on a chain, and it'll still be classified as an alcohol, but each respective hydroxyl group will have to be numbered and listed out in the IUPAC naming. If the alcohol is the highest priority functional group, then the attached carbon has to get the lowest number possible. Phenols are dictated by ortho, meta, or para descriptions. Ortho being directly adjacent, meta being one off, and para being straight opposed. So let me draw these out for you. If I were to have a benzene and an OH here, ortho would have a position like so. So this would be denoted by an O at the start of the name. The meta is one off, so it would be here, denoted by the M. And lastly, para, which is directly away, and this is denoted by the P denotation. Depending on ortho, meta, or para designations, the functional groups are going to affect the reactivity of the alcohol respectively, and the phenol. Physical properties of alcohols. They are capable of intermolecular hydrogen bonding. This leads to significantly higher boiling points and melting points than that of their respective parent hydrocarbons. Note that the more hydroxyl groups present, the higher boiling points. This is because the hydroxyl groups will interact and hydrogen bond amongst themselves, so having more of these is going to increase the strength. These can also act as acids, but the strength is dependent on the structure and the resonance. If there's more resonance to stabilize the negative charge, it's going to lead to a higher acidity. This is most present when it comes to the hydroxyl groups on carboxylic acids, which we will go over in a later lecture. Now that we've gone over the fundamentals of alcohols, let's go into some of the reactions, starting with oxidizing reactions. The first reaction we'll talk about is pyridinium chlorochromate, or PCC for short. PCC is going to oxidize alcohols and make them into ketones or aldehydes. Note that PCC is the only oxidizing reagent that is not strong enough to readily oxidize alcohols into carboxylic acids. This is a very important distinction to make. Chromium does the same thing as PCC, but this is a lot stronger of a reagent. If you are to put this into a terminal alcohol, you will likely create a carboxylic acid because it's going to oxidize until it is fully oxidized. And the Jones oxidation is much the same. If you put this onto a terminal group, you will likely oxidize it entirely to completion, which you can note at the bottom in the cyclobutane reaction. Mesylates and tosylates. These can make hydroxyl groups into better leaving groups, and they serve as protecting groups for alcohols to prevent reactions. What you will do is you'll put the alcohol into a solution, create a mesylate or a tosylate from it to protect the group or to make it a better leaving group. So what's going to happen is if you want to put this through a more complicated reaction, you will protect the alcohol and then just remove the protecting group later on. Speaking of protecting groups, let's talk about them further. Dialcohols can be used to protect aldehydes and ketones, and this can be reversed in a deprotection reaction as well, using simply water and some cationic H+, usually something that's slightly acidic. This is useful for more complex syntheses. Below is an example of this protection. If we are to protect the topmost keto group, the one on the cyclohexane, we will just use a dialcohol and chain it like so. This will let us manipulate the bottom group without messing with the top group. This is useful when we're dealing with more complex syntheses. Reactions of phenols. The first and really only example that's going to be seen on the MCAT are quinones and hydroxyquinones. Hydroxyquinones are less electrophilic than quinones, so take note of that. The structures for quinones and hydroxyquinones are listed below in their respective example. The primary group we need to talk about, though, is ubiquinone, or commonly called coenzyme Q. Coenzyme Q has the distinction of being a participant in the electron transport chain and is thus very important. It can also be reduced to ubiquinol, and if you're curious what that reduction is going to look like, just refer back to the previous slide. The oxidation reduction capacity of ubiquinone makes it ideal for use in electron transport. Other biological molecules that will undergo oxidation reduction reactions as part of their normal functions will be NADH, FADH2, and NADPH. These molecules accept and donate electrons readily, very similar to ubiquinone. So that was short and pretty quick, but that'll cover what you'll see on alcohols and their functions and reactions on the MCAT. Note that the next couple reactions and functional groups that we will talk about in further lectures are going to be a little bit more in-depth. So be prepared, and please join us next time as we talk about aldehydes and ketones.